Thanks a lot for this chance to talk to all of you. I'm happy you're here. If I'm very, very boring, you can study the beautiful room and have some fun with that. I thought for a while about what I wanted to talk about at a conference like this. And there are so many different tracks and so many different topics that I thought if I picked a single technical topic, I'd probably be boring to a large percentage of you. So I try to pick something that's equally boring to all of you because you've all done it all the time, which is what I always like to do in keynotes. I like to pick a topic that seems very obvious. I like to pick something that we don't even think about anymore because it's become what we do all the time anyway. And then I try to find something new or interesting or worth our time, and you'll be the judge of whether I manage to do it this time. I thought this time I'll talk about size of things, about how to split up our systems or the things that we build into smaller pieces. Because I think that is at the core of a lot of the things that we do. We think about how to structure our programs, we think about what goes together, what should be split apart, and we do that on many, many different levels. So this is what this talk is going to be about. So let me start by talking a bit about that title. What am I actually talking about? What is this stuff that we're cutting into pieces? It can be a lot of different things. If you look at the history of computer science and of software engineering, you see a lot of different building blocks. Or if you want to, you could call them construction principles, if you want to be fancy. The things, the ways we have of structuring our work. And there are lots of different things, and they all share a bunch of properties. So let's start with procedures. That was an invention at one point in time. It's interesting to look at something so very, very obvious like structuring our code into subroutines or procedures as something that wasn't available to the first people who programmed machines. Right? So you had to build everything with go-tos and jumps, and somebody introduced the procedure, which obviously raised the question of how big should a procedure be? When do you introduce new ones? Do you want to have many of them? Do you want to have just a few procedures and functions? Then we have something bundling procedures and functions together. Maybe it's called a unit or a module. In fact, modular programming was an invention. It was something that was debated. It was something people went to conferences to hear people talk about, a module as a new concept. I'll get a bit into that a little later. So again, the same question, where do our procedures belong? Do they all go into one module? Do we want to have many modules, small ones, big ones? What's the right unit? You all know the concept of libraries. Now we're entering the 70s and 80s, right? Where some of us at least were alive. So we have this idea of bundling stuff in a way that allows us to reuse it nicely, right? We have somebody who has built a library that we can just incorporate, and as a smaller unit, we have objects, right? Even that, I'm not talking about objects in the object-oriented sense. I'm talking about objects in the sense of the things that you link together to form a program, right? If you've ever built a program in C or C++, you know what I mean by that. Then we had this idea of components, right? We have a new thing, and component, I think, is the first instance of something happening where somebody needed a new word and couldn't find a good one. So they just picked a generic one and assigned special meaning to it, which usually doesn't work. Every time you do that, every time you pick a word like that, you find out that many people understand whatever they want to under that term. And this is the first instance that I personally remember, right? A component can be anything and nothing. It can be whatever your vendor wants you to buy from them. So they just assign an arbitrary name to that. But components to many people had a definition, a runtime environment, a component environment into which they are deployed, right, as a new kind of building block. We have dynamic libraries that are composed with the actual program at runtime or shared objects depending on the platform. We have the idea of images, not even talking about images in the sense of VM images, we'll get to that in a second, but sense of Smalltalk images. If any of you have ever built programs using Smalltalk, the idea was to have this whole thing in an image that was the complete environment, including the programming environment, potentially, that you ship to your users. And now, these days, we're talking about containers, right? We have some sort of containerized solution, or maybe we have VMs, or we combine this with logical things and talk about services, or even microservices. And the newest instance would be a Lambda, which is, I think, the Do I have it actually? Yes, I do. The Lambda is kind of the newest instance of this whole approach, where you have this deployable mini super small unit that you can put somewhere. Every time it's the same discussion. How big do we size those things? And if you look at all those very, very different concepts, you can see a few commonalities. They have a few things in common. One is that they all have a boundary, right? There are things that are within, things that are outside of this thing we're talking about. Right? And that's a conscious decision that you make. Do I put this into a new module or a new procedure, a class, or whatever it is? Did I actually have class on the last slide? Otherwise, just add it to the list. Right? We have this concept of context, right? From a logical perspective, as well as from a physical and from a programming perspective, of things that are inside and outside. That's a very, very important decision that you make. We have dependencies between those things because one relies on the other in some way. It can maybe depend on it being available at runtime, can depend on it being available at compile time. It can make it can have a relationship in the sense of that it instantiates something, or it can call or invoke something in another place. It always does that through some kind of interface, because you have to go plug through that boundary, go through that boundary somehow. And it always runs in some sort of environment, right? Those are the things that are common to all of those concepts. And every single one of those things has an implementation, right? And this implementation is also of importance even if you only look at the interface of things. Sometimes you believe that something is an implementation detail and it doesn't matter when this assumption that this is true just bites you somewhere you don't want to be bitten very, very badly, right? Because you're not aware of the ballast, of the weight, of whatever internal thing you have to incorporate to reuse one of those things. So we talked about lots of different things. All of those things have certain aspects in common. Now, how big shall each of them be? It's very easy. In fact, we can cut this short, have an extra half-hour break by saying just make them the right size. Right? It's very easy, just the right size. This is kind of the holy grail, I believe. Right? I've had this discussion so many times. We talked about well, we've heard many presentations about components, and we totally buy into the idea. This sounds awesome. Now we just need some help deciding how to cut our system into components. Is it 3 or 5 or 500? What's the right way? Why is it so hard to do that? What is the benefit? Let's first start by looking at what we're aiming for, right? And this I'll always like to do with my favorite programmer story. I do hope that all of you know the protagonists of the story I'm talking about. There was a contest in a magazine. It was a long time ago, I think 25 or 30 years ago. And in that magazine, they proposed a simple programming task. Right? This is a very simple task. You have a file, it has lines of text, and you want to read in that file, and you want to find out how often words occur. And then you want to print out a sorted list of the most common words together with the frequency with which they occur. Okay, that seems like an easily doable kind of thing. Each of us could probably program that in a limited amount of time. Now, they didn't ask us to program this thing. They picked two more interesting guys, these two. I don't know how many of you know both of them. I hope that all of you know Donald Knuth. That is the author of that book you've never opened, but which sits in your library, right? The Art of the Computer book. No, it's probably a great book. I can't claim I have read it, but I've skimmed it occasionally, and it actually sits in my library. But Donald Knuth is a very impressive person, and I have listened to some talks and read some articles and stuff that he's written. He's a super smart guy. He also happens to be the author of Tech, which he wrote because that's what you do if you want to write a book and there's no decent software to write a book, then you write the software to write a book. And if that software needs a good way to present fonts, then you invent fonts on computers and you actually create Metafont, a program. You spend the next 10 years just building the infrastructure to write the books you actually want to write, which is like the original invention of yak shaving, just from a more academic perspective. So Donald Knuth is a superman in terms of computer science. He's probably the world's best computer scientist. And he did this task with a fantastic piece of code. It was a literal program, which is his invention, was one of his inventions. It's the idea that you mix documentation and code, and he had this fantastic program to do this. And by the way, he just invented a few data structures and algorithms, because that is what Knuth does, right? It was probably the best thing. And the other guy was Doug McIlroy. Who knows Doug McIlroy? Anybody know who that is? Nobody? He invented a very cool thing. He invented a vertical bar. He invented the pipe, right? That's one of the original Unix dudes. And he invented the pipe concept, the piping concept, and that was his solution. Now you'll notice this solution has almost as many lines as almost exactly the same number of lines as the description of the program that Knuth wrote, right? So what it does is it uses standard Unix commands, which replaces one character with another character according to this list, right? And then it pipes the result of that. The first one actually does kills the line feeds. The next one translates uppercase to lowercase. Then we sort everything. We filter out the uniques and we count. And then we sort it by the result of the count. And then we just make sure that we print it correctly. That is actually what Doug McIlroy did. And that is what we're striving for, right? We want to have those simple, combinable, easy programs. And that's why everybody keeps talking about the Unix philosophy when they talk about their microservices and whatever fancy strategy of the day they want to sell you, right? So this idea is very powerful. It seems very powerful. You have small pieces and you can just join them. Now, I think that glosses over some details. I don't know how many of you regularly do this kind of thing. I actually do it, and it works until my program is about 200 characters long. Anything longer than that, I have no idea what it's doing, and especially I have no idea why it's breaking. Right? It says broken pipe, and I have no idea why. I cut it apart and I try to figure out what happened. It's not very failure tolerant. It's not the way you want a nuclear power plant control system to be built. You don't want to do that. And I think there is a reason for that, and that reason has been elaborated upon by another very, very famous guy that you should know. I've put a picture and his name in there for you. So Mr. Parnas, probably Dr. Parnas, I don't know, Professor Parnas, invented or described this principle of information hiding. That is actually a fantastic paper. I recently reread it when I prepared this talk. I read it maybe every 5 years or so. Pick that up and just read it. It's fantastic. It's from 1971, and it explains how you should structure your programs, and it tells you why we do things the way we do them today. So the key idea here is that you don't just separate your program into one step after the other, right? You don't look at the program, at its input and its output, and then you write 5 parts, and then you cut down the first part into 5 others. You try to structure those parts around something that you want to hide. That typically is some sort of design decision. You've made a decision to use that kind of data structure. You have made a decision to use a file. You've made a decision to use, I don't know, some library, some framework, some sort of technical dependency, right? You make some design decision and you encapsulate that in this particular thing. That is the idea of information hiding. It's not just hiding a data structure, it can be anything. Actually, this program that he describes is actually something that looks like this, and he transforms it into something that is way better, right? He transforms it into something that survives change, which is, I think, one of the key ideas, right? You want to be prepared for certain kinds of change, and you want to be able to react to that change without having to rewrite everything. That's why we do things this way. As we're talking about famous people, here's another one. Hope you know him. He's also written a ton of fantastic stuff. He's the most quotable computer scientist. He was the most quotable computer scientist, I think. To his credit, he coined the term, among many others, separation of concerns, which you've probably heard. I find it interesting, as I looked up where he actually did that, I found that he explicitly did not restrict it to the idea of having a program, right? A program that addresses just one concern. To him, it was a way of thinking. Right? It was the original way of thinking, was the scientific way of thinking. You focus on one thing and you don't think of everything else at once. Right? You focus on this one thing, you address this one aspect, and then you look at another aspect, and you try to address things with a focus on specifics, and you separate concerns. That, I think, is one of the key things that we do. We separate separate things. Right? If they don't belong together, we tear them apart. Well, we don't have to tear them apart because they don't belong together, right? We don't stick them to each other. We just leave them to their natural separation. That's what we do when we separate things. Which, of course, on the other hand, means that we join things that belong together, right? If something should be in one unit, it's a pretty bad idea to put it into two different parts, right? The separation idea has become mainstream, right? The idea of having a separation of concerns, or as this dude calls it, the single responsibility principle, I think is a very common thing, right? The single responsibility principle, I believe that term actually comes from Bob Martin. Originally was applied to a class or a module, but you can view it more generically, right? Do a single thing and do it well is the original Unix philosophy according to Doug McIlroy, the pipe guy. Right, so the idea is here that you have only one reason to change this thing. If there is more than one reason to change it, more than one potential reason to change it, then it does more than one thing. That is the concept. Just make it really small. Also very interesting is this corollary, which says you have to make the right guess. Right? If this change never happens, if you pick the wrong axis of change, and then no change ever occurs along that axis, you've made a wrong decision. You've modularized along the wrong axis. So, again, throwing around terms that you've all heard, and I think it's interesting to look at their origins, right? High cohesion, loose coupling. That sounds awesome, right? If you manage to have that, everything's great. That's what you should aim for. High cohesion, loose coupling. What the hell does that mean? What does cohesion mean? I'm not a native speaker. I have to sometimes look words up, and I was inspired to do it in this case because somebody else, a native speaker, did it, a guy called Glenn Vanderberg. And he looked up some words that sound similar but mean very different things. The first one is adhesive. Adhesive, adhesion, to adhere. Adhesive is if you stick something together, maybe using some sort of glue, right? It becomes sticky, and now you have made an effort to make it stick to each other, right? That's what you do if you somehow combine things, right? And there's another aspect, it's a very different thing, which is cohesive. And cohesive means characterized by causing cohesion, which is one of those meaningless definitions that drives you crazy, so you look up cohesion, right? Cohesion. Cohesion actually means that it is, well, it's united, right? It is a united whole. It is parts, but they have to be together. I like the physics definition even better, right? That's absolutely perfect. The sticking together of particles of the same substance, right? It is of the same substance. That's why you have to put it together. If you tear it apart, you do something bad, right? You also have inherent, which is also nice because it has similar roots, right? And this essentially means this is impossible to tear apart. It is just an intrinsic, what's another word? It's just an inherent part of something, right? It is absolutely inseparable, right? That is the idea. Those forces that help you decide when to put something together, when to tear it apart, obviously are in a position, right? You have to find the right balance until it feels good. And a great exercise, if you are OO programmers, which I assume, how many in the room program with Java? How many of you are doing that? That's the majority. Scala, anybody? Some, okay. That's enough OO for my taste. If you do that, then there's a great exercise called object calisthenics. That's exercise, right? A physical exercise. The kind of that you do every morning, right? That's calisthenics. And this is the idea. It's actually by a guy called Jeff Bay. It's pretty hard to dig that article up, but you can follow that link and you'll find an older version. It actually is a set of rules that you are supposed to follow for a limited amount of time. So this is not advice for your production systems, right? The idea is if you're at a hackathon or at some kind of programming event where you have a day or two, just adopt those rules. Don't question them, don't discuss, don't go on a meta level, just go ahead and do it. If you do that for a day, your mind will be changed. Unless you've programmed Smalltalk in the 90s, then you'll say, duh. But if you've only ever used an object-oriented programming language like Java or C++, this is eye-opening. It includes concepts like a class should only have, how many does it, one or two instance variables. If a class has more than two instance variables, it's too big. No class should have more, because the instance variables in a class are actually global variables shared by all the methods in that class, right? So they're put there and they share some state, but if that state is too big, then it's actually 2 or 3 or 5 classes hiding in one. And we all know the problem with big God classes, right? So it's a very interesting exercise. There are a number of indicators of strong cohesion, right? If something is cohesive, then it is probably simple to understand because it just does one thing, right? It's all this cohesive forces around this one idea. It is simple to explain, right? Because it's easy to understand, it's simple to explain, obviously. It does one thing, right? That's the single responsibility aspect we already talked about. It probably has one stakeholder. There is one person, or maybe one kind of person you need to talk to if you want to change something in this particular thing, right? Because it's focused, it only addresses this one aspect. It's hopefully difficult to split because if it were easy to split, then it wouldn't be cohesive, and is only reusable as a whole, right? Or usable as a whole. You cannot use part of it. It doesn't make sense to use parts of it. If I want to use parts of it, I'll probably want to use all of it. And it's very obvious that if you look at the forces making you put things together, then you can look the other ways. You know, what is an indication of weak cohesion? When have you put stuff together that shouldn't have been put together? Obviously, if it's hard to understand, this is boring, right? Hard to understand, difficult to explain, many reasons to change, many stakeholders, partially reused, or if people want to partially reuse it, and obviously divisible. Now, of course, that is not helpful at all, and I'm totally aware of that, right? This is just, you knew all of that. Let's look at in more detail this particular thing. I think if we look at division, if we look at the way we can decompose things, which, by the way, is a funny word, right? Decompose can mean split into parts, but decompose also means rot. Right? Decay. If something decays, then it's decomposing. So maybe it's not that fun activity, whatever. I'm talking about cutting things apart here. So if we look at the forces that do that, then we can see that they are very, very different. Right? You can look at different forces for separation. One of them is you have different environments. That's not an obvious one. That's not what you thought about when I spoke for the last 10 minutes or so, because it seemed I was talking just about code. But think about this as a force for separating things. Right? You have these things, they seem to be cohesive from a logical perspective, but from a physical, from an environment perspective, they are very different. This is a credit card number. You are not supposed to store credit card numbers. And if you do, you have very, very strict regulations to follow. So maybe you should split that part and cut it out and separate it from the part that just stores an address. That's not obvious. Right? That's a different kind of technical need. It might scale differently, right? This part is hit by 1 million users. This part is hit by 5 back office assistants, right? These are very different things. They might seem cohesive, but they're not because they have different aspects. Right? Cross-cutting concerns may force you to separate stuff, right? Because it's something that seems orthogonal. That's the whole idea. You'll see that phrase come up more and more often, cross-cutting, orthogonal dimension, because it tells you that there are things going in different directions at the same time. And it's pretty hard to come up with the right decision there. Right? You might want to reuse parts, but not others. Maybe you want to separate the reusable parts from the non-reusable parts. Maybe you're building a product line, maybe you have different customers, different clients, and you want to separate the stuff that you can reuse from the one that you can't. The frequency of change, maybe it is the same stakeholder, but maybe the frequency of change is very different because one thing is related to products that you sell and the other one is related to, I don't know, tax regulation. So you maybe want to separate that even though it might be the same people interested in that whole thing. You might want to isolate development. You cut things apart for the sole purpose of enabling different teams to work on it. It's a very tough decision, right? If it's cohesive, if it should be together and you split it apart because of that reason, that's going to go dramatically wrong because the team will have to talk to each other all the time. But if you have a force here that tells you, I need to split this because, I don't know, maybe some regulation, maybe somebody's job is on the line, maybe you want to make sure the Berlin office is still there next year. For whatever reason you want to split stuff, then this can be a force, and it might be a very, very opposing force to the others. That's actually the root of Conway's law, right? Every architecture presentation these days has to include Conway's law. This one's no exception, right? It says that architecture and organization are very closely related. Let's leave it at that. You might want to have isolated runtime environments, right? You might want to be able to, maybe for scalability reasons, but maybe for deployment reasons, maybe for release reasons. Maybe one thing, because of a different frequency of change, has a different release cycle than another thing. You might have different technical dependencies. From the business side, everything's fine, but this piece of code, this part of the code depends on a huge library, and this part doesn't. And maybe you don't want everybody to suffer from this huge library because they have to download half the internet. If they want to reuse it, you just separate things because the dependencies are different. What did I add? Damn, always happens with these things. Domain dependencies are a similar thing, right? You have a dependency on a particular domain decision that you maybe want to hide from others. Or you have implementation aspects. You do not want this implementation to share an environment, a module, a service, a system with another implementation. Right? Weight is another thing, right? Weight in the sense of, this is one of those, do you know the term SODA? Stack overflow-driven architecture? Where a system grows, and because everybody just keeps adding stuff they find on Stack Overflow, everybody just copies stuff in it. They pull in library after library, and you have these, hundreds of megabytes of libraries that you have no idea what they do and who wrote them, what license they're under. If you have those kinds of systems, maybe they've become too fat. Maybe you want to separate that from others. So we have multiple dimensions with different priorities, right? Multiple dimensions. You can't be right. You can't do the right thing. Just have to accept it. Right? There's no way for you to satisfy all of those things at once. You have to find out what the right decision is. One thing that I've been talking about a lot with a lot of projects in recent weeks and months is this idea. You have a system, one single system, because that's what God told us to build, a single system, and we have layers, because that's the way we do things around here. And then we have modules, right, that obviously follow the structure. So every module has this, and it's all a single system. And maybe that's just stupid. Maybe that's not what you should be building, right? Maybe what you should be building is free systems that maybe have this layered structure, right? But the module thing, which was secondary, or which was actually the third thing I talked about, now becomes the first thing. Can you see the difference in the order of applying this carving up at different dimensions? This is what I think is a much better architecture than building a single system in many cases. Not always, obviously, but in many cases. Sometimes things are fractal. I just picked this because I like the picture so much, right? You have this idea of things being composed of the same thing, being composed of the same thing again, and that is true on a theoretical level, right? If we're talking about a UML package or even a Java package, we can see this composite structure, right? Something is composed of itself. But that's not really true universally for the things we build. If you look at the things you build, you typically have something maybe like this. You have different kinds of things. This is just an example, right? Different kinds of things with maybe some rules attached. Whatever it is, doesn't really matter, right? You treat a module different than a class. Maybe you don't have a module, it could be a subsystem, or maybe that's what you use a jar for, whatever. It doesn't really matter. You have your idea of what your architecture is like, your idea of how you want to build things, and then you attach some rules. And that is a system that constrains, in a positive sense, your ways to express yourself, right? You have you maybe with your colleagues agree on this. Maybe you have a fancy architect who comes up with this. It doesn't matter. Either explicitly or implicitly, you have something like this, right? This is the shared model of thinking of your system. And you can see that there are different levels of modularization, right? We cut things apart different on the upper levels than we do at the lower levels. Right? Things that are maybe methods in the same class have a much closer connection than classes in the same package, than classes in this different packages, and so on and so on. Right? So if you look at that on different levels, then obviously there are different rules and strategies for doing that. Now, one thing that I've noticed is that if you look at this in many large projects, you have something like this and then maybe you change it at some point in time, right? You add something, maybe you have this service thing because somebody said service orientation is totally cool. Maybe they even don't do that anymore, but a few years ago that was what everybody did. Maybe now it's a microservice. So everybody introduces that, and now we have this evolving model. It becomes more and more complicated, and then we put one of those things next to the other, right? Well, maybe not. Maybe at the year we notice that, well, now that we've introduced this service kind of thing, maybe we don't need another structuring level below. You know, if you have a single system, then you have a certain need for modularization within that system. If the system grows, the need for modularization becomes larger. Maybe if you split the system apart into smaller units, you don't need some of the modularization levels, right? A good example would be EJBs. Now, whatever you think about enterprise Java beans, I don't really care. Let's just assume for a second they were a good idea. Then obviously they were a good idea. What? Obviously they were, I believe they were a good idea at some point in time. I believe many things that I no longer believe in, but whatever. At some point in time, people thought they were a good idea for structuring a large system. And then when different ideas come up, maybe they're not needed anymore. Maybe you don't need that level. You can directly go from whatever abstraction you put on top to the one below. And maybe this just means leaving out one of those structuring mechanisms. Maybe it allows you to change things completely, right? Maybe whatever, this is a stupid model, but whatever idea it is that you have, whatever technology you want to try out, whatever model it is you want to apply, you can apply it because you have a different thing this resides in, right? So I think that is one of the interesting aspects, that if you have separate modules, then you can have separate modularization strategies within those things, and you should explore that to its fullest. Another thing that I have to mention, because otherwise it seems as if I'm stupid and don't know that the real word is there as well. We only look at those blue things, right, that are connected in some way, it's very, very important we don't forget the rest here, right? It seems so invisible, we don't actually see it, but it's there, right? It's the environment, it is all of the stuff that is just not in our primary focus right now, but that is very important, like transactions and security and scalability and monitoring and logging and a component runtime environment and an application, so whatever it is that you want to put your things in, right? It's very important. If you don't consider this, if you don't make a conscious effort to take that into account, then you have a problem as well. Right? So we have lots of different environments for those things that we cut our systems into. Right? It can be a simple language runtime if we're at that level. It can be an application server. It can be an operating system when our main structuring mechanism is processes. Right? If we have a process, like in the Unix philosophy for everything, then that is maybe a very important thing. If you look at the Unix systems, they don't come with a single big command interpreter that does everything. They come with a very small one that just calls out to other commands, other processes. We could maybe have container hosts of some kind. We could have a hardware, right? We could have different machines, different boxes as a modularization strategy. That seems kind of weird, but maybe not if we're talking about virtual machines, right? If our environment is the supervisors. We have different things that we talk about and different environments in which our systems are deployed, into which our individual things are put into. Okay. So I wanted not only to talk about abstract stuff and leave you completely baffled as to why you wasted your time with me. I also wanted to put in some actual things that I believe are lessons learned that I found valuable. So let's go over them pretty briefly. So the first one is, and I always present them in this format, right? What works and what doesn't. What works is be explicit about your meta model. That's the idea of what your architecture actually uses, right? You have, even if you're in a very small team of 2 or 3 people, it makes a lot of sense to just talk about what the building blocks are that you're using, and to agree on them to a certain degree, at least within that particular scope of that particular team. Right. You've all probably done that in some way or the other when you talked about layers, and when you ever tried to convince somebody that a circular dependency is maybe not a great idea, or that maybe the database shouldn't be calling into the UI code or something like that. You know, if discussions like that come up, it makes some sense to set up some rules. Right? And that works. What you should never do is mention the word meta model. Right? That is a disaster. I only did it once. You know, don't do it. in this presentation. But it still is what we're talking about, right? Don't turn this into an academic exercise. Don't make this into the reason for your being. Just make a quick sketch and say, well, this is what we do, and then just go with it instead of turning it into a science. What also works, and I'm extremely, extremely convinced of this, is separate macro and micro decisions. You saw a hint of this when I presented this system view and this thing of the different modules with different implementation strategies. It's an excellent idea to agree on the macro rules, like to a particular level, and to leave the internals to whoever builds that stuff. Right? Nothing is worse than somebody who tries to standardize everything, right? Which is what doesn't work. If you try to come up with an architecture document, and the architecture document contains every single rule you can think of, down to the last, check style statement, and everything, and if you've nailed down every tool and library and version, everything, that's going to fail. And it doesn't give you any benefit. It just ensures that your software will become outdated as a whole, as opposed to just parts of it becoming outdated. Instead, make decisions on that upper level and leave some freedom to the individuals or to the teams who build at the lower levels. Because that is your strategy for evolution, right? It's a strategy for building new things once in a while. That is also something that does work, because there is a fundamental problem with this whole approach. A good strategy of attacking a problem is to do it piece by piece, right? Divide and conquer. That's what we do. Now, the problem is dividing assumes that you know what it is you're dividing. But that's what you want to find out, right? You don't know whether you've picked the right strategy of dividing something until you've done it. And maybe even after you've done it, you don't really know. Maybe you only know it after you've put it into production. But there is no way around it, unless maybe you're building the second or third system of that kind. But if you're attacking something that is new, you just have to start with something. You have to make a good guess. Trust your gut and just, come up with something that seems reasonable to everyone sitting around the table and just go with it. Separate things and have individual parts evolve separately from each other. You can always change your mind, and you will have to change your mind, right? It's the very obvious thing. You notice that two things, maybe it's two services or two classes or two packages, talk way too much to each other, and then you'll know that maybe they shouldn't be really separate things. Maybe they are just one, or maybe there is one common thing waiting to be extracted. What doesn't work is to ignore this problem and just talk about layers. Right? I've seen many architecture presentations in the initial phases of the project where I was just presented a generic database, business logic, presentation layer diagram that I've seen and drawn 100 times. That's not addressing a particular problem. That is because you don't know how to address the actual problem, you address one that you do know, right? Which is how to play around with MongoDB because you haven't used that before. Right? So that's not a good solution. You have to attack the actual problem, and you have to be brave enough to do that. Okay. This is also an experience, I think, that organization and its use cases, the actual things the organization wants to do or the users want to do, should drive the carving apart. So you separate things into separate units, and you do that according to the triggers that come from the outside. So on the outside, there's somebody who wants to do something with the system, and they don't want to use all of the system, they want to use part of it. It's almost universally true. If you're building a bigger system, there are different stakeholders who have different views, different use cases that they do with the system. And those use cases should be the primary driver of your modularization. That is my firm belief. What doesn't work, that's also personal experience, is centered around technical commonality, and also, and I include things like they all access the same entity. So that is something I've seen maybe 3 times in the last year. Systems where people wanted to extract, well, in this case it was services or microservices, and they centered them around an entity. This is the customer service. And now everybody has to go to the customer service whenever they want to do anything with the customer, which essentially means everybody. So this customer thing now has many stakeholders. It has many reasons to change. It has a completely different change frequency. It has different scalability. It has all of those things that are indications of weak cohesion. It's a stupid idea. Don't do that. Right? Don't do that. You should have multiple customer service things actually as part of the things that you do with customers. So I'm much more in favor of something like order management and product presentation or whatever that does things on a different level. What also works is to prepare to be wrong on every level, right? You have to just admit that you're going to get everything wrong because this is just a guess that you're making, and that's fine. And this is true for things like the implementation as well. Typically, I think that is one of the drivers for this microservice idea. People have noticed that it's hard to evolve their systems, and they believe that using microservices will help them because they can more easily replace them. In fact, there is a guy, I'm going to show you a picture of him in a second, called James Lewis, who wrote a nice article about microservices, who coined the term designed for replaceability, not for reuse, which I think is a very cool idea, right? You don't build stuff that it can be reused 1,000 times, you build it so that you can throw it away. There's another very, very cool guy called Chad Fowler, who I've recently listened to present the idea of throwing away good code. He said, just throw it away every once in a while. Because if you don't, you get way too attached to it. You know, it's like you keep it alive, although it shouldn't be kept alive. You know, just every once in a while, just throw it away. Well, to be able to do that, you have to have small things where it really doesn't matter, right? Make the things so small that if you come across them and you don't really know how they're built, or they were built by that super stupid guy that is smelly and that you don't want to have anything to do with, just throw it away and write it from scratch. If it's doable, I'm not sure I want to go that far, but I like the idea, I like the concept. You could call it active recycling, right? There's the connection to decomposition again, in a different manner. What's not going to work is to aim for perfection and just stick to it, right? It's not doable. Don't accept anybody to be able to do that. And in fact, if you try to come up with the right model, you've made the first mistake already, because trying for a homogeneous model across all of those different things is never going to be what you actually want to do. Okay. So I don't want to steal any more of your actual break. I believe you've earned it. So let me move a bit forward and make it really quick. The only question you're really here for, right, because you read the abstract and you came here early in the morning instead of skipping the talk, is how big should your microservices be, obviously, because everybody's talking about microservices all the time. So let's cut right to that and make it really quick. I wanted to unask this question, say, well, this is actually, we shouldn't be starting with that. But let me elaborate a little bit. There are many answers to this question. There are, in fact, different approaches. There is one answer that says they should be super small, right? This is the Fred George school of thought. If you don't know Fred George, just Google him, watch some of his presentations. Awesomely smart guy. He builds fantastic systems with super small microservices that don't know that they talk to each other. They're connected through a bus. They react to events. Sometimes a single event is handled by multiple microservices multiple times, and the outcome is sort of emerging behavior. It's fantastic. It's really awesome. His microservices have 100 lines at most, 100 lines of code at most. That is one school of thought. And it actually works pretty well with this new approach of serverless architectures. So if you've ever looked into Amazon AWS Lambda, it's an environment for running small functions, this is a perfect match. I think it's cool as hell, and you should be looking at it. Or maybe you should be doing this, right? This is the small kind of school that says, well, they should be, Docker containers, and they should call out to other microservices, and they should do that resiliently and cascading, or maybe in a streaming fashion. And this is kind of the way that you see Netflix describe what they do, which is awesome too. Right? Very smart people. If you watch any talk by Adrian Cockcroft, they talk about super smart things. And there are others as well who do something like that, which is okay. It is different, but it is okay. Why should one of these be the right answer? How could one of them be wrong if people are successful with that? Or is it just about what can be legitimately called a microservice? Well, whatever, maybe just that because it's really micro, right? I don't know. Or you could go with what I like to advocate for, my colleagues do as well, some of them at least, medium size. This is sort of the slightly bigger approach that says, well, we should be talking about those systems, right? Those self-contained autonomous systems with their own UI and their own database they are an order of magnitude larger than the next category, so that you maybe end up with 7 or 10 for a large system, as opposed to 100 or 1,000. Right? And that's fine as well, I think. So they could be composed of smaller variants as well as the others. You could use one strategy there, the other one there. Right? If you want to read more about this approach, we've put up a little website called SCS Architecture that outlines some of those principles as well. What I wanted to get across is that if you look at those things, it's fine to have multiple aspects and it's perfectly fine to combine them. Just be aware of what you're doing. And that's basically all I have. I promised you this picture of James Lewis. I asked him to send me a picture because I wanted to quote him, and he sent me this whatever. I like him a lot. That's all I have. It was fun talking to you. I'll leave you to your break and enjoy the conference. Thanks.